All right, so the last thing that we need to talk about that you're going to see on your test Friday is this enzyme, the energy part of the enzymes and energy PowerPoint here. Some of this we already talked about. Got to learn how to do a little bit of math. We talked about energy several times. We said energy is the ability to what? Do work, or another way to think about it, to make things move. And in one way or another, with very few exceptions, pretty much all the energy on Earth comes from the sun. Now, before we go too far into this, I want to review something that's not directly related to what we're doing, but something that shows up in like ecology. So let me put in a slide here. This is something you should have seen like in elementary school, I hope. I'm going to put in a pyramid here. Did you find out? Mm-hmm.
Yeah.
All right, this is like a food pyramid. Not like the food pyramid you eat, but like a food chain kind of pyramid. Sometimes it's called an energy pyramid, or you might say called a trophic pyramid. Trophic means like feeding. And in this kind of pyramid, what's always at this bottom level?
Plants. Everybody else.
All right, so I heard somebody say plants. What's more of a sciencey word for that? Producers. We might call them the primary producers. Things that can do photosynthesis too. Why is this level at the bottom so much wider than the ones as we go up? There's more what available? More energy available, because these things can use what? Sunlight. So I'm just going to make up a number here for energy. Let's say that they have 100,000 joules of energy available to them, the plants, the producers. 100,000 joules of energy. I just made that number up out of the blue. What's the next level called? They are the primary consumers, the first things that actually eat other things. Primary consumers. And here's the important thing to get from this pyramid. About how much of the energy that starts in this level is actually transferred to the next level for those things to use. It's about 10%, 1 in 10, which means 90% of the energy ends up where? It's either given off as heat or it's in the waste products somehow. Got pooped out, never made it to the next level. So what's 10% of 100,000? About 10,000. So out of the 100,000 that the plant started with, only about 10,000 joules of energy make it to this next level. Sometimes it's called the rule of 10. It's not a hard set 10%, but that's an average number. What's the next level called? Secondary consumers. And how much of this 10,000 makes it up to there? 1/10, 10%. So about 1,000. And then what comes next? Tertiary. And about how much energy is available there? About 1/10 of 1,000, which would be 100. And then what's the top level called? Primary, secondary, tertiary, quaternary, like a quarter, quaternary, fourth. It usually doesn't go much further than this. How much energy is available up here? Only 10. Why doesn't it go much further than that? There wouldn't be enough energy, right? The reason the levels get smaller as you go up is there's less and less energy, and therefore there can be less and less things, right? There can be less and less organisms because there's not enough energy to sustain them. If we were talking about like a cotton field out here, over there, what would be like a top level thing in the cotton field? Maybe a hawk, maybe a big old snake. How many hawks or big old snakes are going to be in that cotton field?
1 or 2.
Not very many. Okay? Because by the time it gets that high up in the food chain, there's not what? Not enough energy to keep many hawks or snakes alive. It limits their population size. Decomposers. That's a good question. Where are decomposers at? They could go in at any level, really, right? Well, that's why we don't really show them. Because they could eat these things when they die. They could eat these when they die. They could eat any of them when they die. So we usually just don't show them in the energy pyramid. Everybody okay with that? All right, let's back up a little bit. We talked last time about some laws of thermodynamics. And the first one, first law of thermodynamics, essentially is sometimes called the law of conservation of energy. It says you can't what? You can't create or destroy energy, but you can what? You can transfer it from one place to another, or you can transform it from one kind of energy, like maybe potential, to maybe kinetic, or to heat, or to sound, or to light. You can transform it from one kind to another. That you should have heard about a lot over the years. The second law you probably haven't heard about as much. It's about a concept called entropy. 2 or 3 ways you might hear this talked about. One of them is that the amount of entropy in the universe is constantly what? Increasing. The universe is becoming more and more chaotic. And a lot of that is because when reactions happen, what do a lot of those reactions give off? Heat. And heat makes things move out. And randomly. And that's what entropy is, right? Random, it's chaos. Another way to think about it, if everything wants to become disordered, how did things on Earth, like your body, become so ordered? How do you maintain the order of your body? Is a pretty ordered thing. Nature doesn't like that. How do you maintain order when nature wants disorder? You have to use energy. So a useful way to think of the second law in terms of biology is that energy must be added to maintain order or to maintain homeostasis. That's a good way to think about the second law when you're talking about biology. You've got to constantly add energy in order to maintain order. All right, something else that we need to talk a little bit about is ATP. And we've talked about it nearly every day all semester, so we'll hit it a little bit more here. You know, it's adenosine triphosphate. Think of ATP like the energy currency of your cell. It's like money in your cell, because it makes everything in your cells happen. It's kind of scary that we only have about 20 seconds worth of ATP stored up. So if cell respiration stopped in your body for more than 20 seconds, it's over. And there's no coming back from that. You're dead if you run out of ATP. Why do we only have 20 seconds of backup power? Yeah, ATP is a really reactive chemical. So reactive that you can't store it. You really can't transport it very well. It's too reactive. So we're completely reliant on doing cell respiration constantly. And if we ever stop, that's a problem. If we go down a little bit further here, we're talking about the hydrolysis of ATP. Arguably the most important chemical reaction in your body. What's hydrolysis mean? Break it down using the help of water, right? Using water to break things down. Why would we want to break down ATP? That's how we get the energy out, right? What do we need to take off of an ATP to get the energy? Take off a phosphate. And what are the enzymes called that transfer that phosphate from ATP to something else? No, it's not senior messengers. Protein kinases. It's an important term to know. They'll take a phosphate away from an ATP and they'll give it to something else. And what does that phosphate carry with it? It carries energy. It's a way to transfer energy. Now this reaction, the hydrolysis of ATP, would it be exergonic or endergonic? Would the hydrolysis of ATP be an exergonic reaction or an endergonic reaction? What's exergonic mean? It releases energy, right? Energy that can be used by other things. ATP hydrolysis is exergonic. It gives off energy, releases it. Endergonic reactions, on the other hand, they have to have energy to get started, right? They have to have energy to go. All right, here's sort of how ATP works. Now there's a typo on this slide. That shouldn't say ATP, it should say what? It should say ADP. Just a mess up in the slide. Here's ATP. I want you to think of ATP like a battery that's charged. This is a charged up battery. And then going this way, what are we doing to that battery? We're using it. ATP is used to power what in your body? Pretty much everything. But a lot of the reactions in your body are endergonic. For those to happen, you have to have a steady supply of what? Energy. So this ATP hydrolysis provides the energy to make these happen. And a lot of times, this is an important term. We'll say that ATP hydrolysis is coupled with an endergonic reaction. Coupled with it. They're a pair. The ATP gets broken down, and then the energy from ATP hydrolysis does what? What would the energy from the ATP hydrolysis do? Make the other reaction happen. They're coupled. They're a pair. Exergonic reaction coupled with endergonic reaction. Exergonic makes the endergonic one go. Right. But back to my battery analogy here for a minute. Think of ATP like a charged up battery. Going this way, we're using that battery. We're using the energy in that battery. And we end up eventually with ADP and P, which are like what? Like a dead battery, but a rechargeable battery. And what this process over here that recharges your battery, what's your recharging process called? That's what cellular respiration does. It recharges batteries. And the energy to recharge the battery comes ultimately from where? From your food. That's why we eat. We eat food to get energy to make more ATP, to recharge our batteries. So that's the ATP cycle, and that's something we talked about nearly in one way or another nearly every day, but it's important to know that. ATP hydrolysis is an exergonic reaction, and it provides the energy to make nearly all of your body's endergonic reactions happen. Here we can see an example of that. Here's ATP hydrolysis. You said that's ender or exergonic? Exergonic. It's releasing energy, right? And the energy that it released is then absorbed by this reaction. This reaction is what kind of reaction? Endergonic. But that energy that this gave off is then used to take C and D and make them into A and B. These two reactions are coupled. The exergonic reaction provides the energy to make the endergonic reaction happen. They're like a pair of partners. Here's another example. Got ATP hydrolysis going on here. Exergonic reaction providing the energy to make your muscles contract, which is endergonic. Without this, this can't happen. They're coupled. They're a pair. All right, now here's where we're going to get to something that if you don't listen to me, you're going to get confused on. We're going to talk about something called Gibbs-free energy. This is where the math comes in. How many of you have had AP Chem or you're in AP Chem? You guys have heard this in a much more complicated way than I'm going to approach it. I'm going to try to keep it simple. Essentially, I've told you guys this several times, the most easy thing on the AP Biology test is the math. It's essentially plug into a formula and get an answer. If you can plug into formulas, you can do AP Biology math. This is an example of that. But you got to understand the concept first. Gibbs free energy. Free energy. First of all, I don't like that word because is any energy really free? No. They used to call it available energy. It's energy that's available to you so that you can use it to do what? To do work, to do stuff in your body. So it's energy that's available to you to do things. That's what free energy is. Where do you get free energy from? You get it from food. Okay? That's where your free energy comes from. So essentially you eat the food and then you convert the food energy into what actually powers all our stuff. Convert food energy to ATP, and then we use the ATP as our source of free energy. Now there's an equation that goes along with this idea of Gibbs free energy. And here's that equation. I'll write it in symbols up here. Delta G, that's Gibbs free energy. He's the guy who figured it out, Gibbs, is equal to delta H minus T times delta S. And again, we could talk, there's whole classes on Gibbs free energy in college. You don't need to go there. We're going to keep it simple. Remember, this is Gibbs free energy, the energy available for you to do things with, for you to do work. This delta H is called enthalpy, or sometimes the total energy in the system. Total energy, enthalpy. The T. Whenever we're doing math and biology and temperature is involved, what kind of temperature has it got to be? It's got to be the Kelvin temperature. So this is the Kelvin temperature. And then delta S, that's called entropy, change in entropy, which we said is a measure of what? Disorder, chaos, randomness. And you've got to know what each of these things stand for. If you know what each of them stand for, you can work the math. Again, Gibbs free energy equals to delta H enthalpy minus the Kelvin temperature times the entropy. The key thing you need to understand, if you calculate a delta G and your answer comes out to be negative, that tells you some things about the reaction you're calculating it for. If you got a negative energy value, what do you think that's telling you about the reaction if it's negative? Is it taking it in or is it giving it off? Turns out negative means it's giving it off. So if you get a negative delta G, it's a reaction that's releasing energy. If it's releasing energy, it's what kind of reaction? Exergonic. So negative delta G tells you the reaction is exergonic. Some of that energy that it's releasing is probably heat. And what do we know heat makes things do? Move, and move how? Randomly. So what's it going to do to the entropy of the system? It increases entropy. So far a negative delta G has told us three things. It's releasing, the reaction is releasing energy, which means it's an exergonic reaction, giving off energy to the environment. It's increasing entropy. And we might also say that the reaction is a spontaneous reaction. What does that mean? It's spontaneous. Yeah, it happens on its own. Now, you still have to give it a little what? You still have to give it a little bit of activation as you get it started. But once it starts, what happens? It goes all the way. Think of it like a little kid sitting up on top of a slide. You give that little kid a push, what happens? He goes all the way to the bottom. Okay? That's a spontaneous reaction. If on the other hand you had a little kid at the bottom of the slide and you're trying to get the kid to the top, what do you got to do the whole time? You got to push him the whole time, right? What kind of reaction is that? When you got to constantly add energy to keep it going. What would be the opposite of a spontaneous reaction? How about a non-spontaneous reaction? Okay. But so far, here's what we know. We know that if you get a negative delta G, a negative Gibbs free energy, the reaction's giving off energy, it's exergonic, it's increasing the entropy of the system, and it's spontaneous. That once it gets started, it finishes. Now, if the delta G happens to be positive, if you do the math and you get a positive answer, all the opposite things would apply. So if delta G is positive, that means that it's doing what with energy? It's absorbing it. It's taking it in. And if it's absorbing energy, it's what kind of reaction? Endergonic. So positive delta G tells you got an endergonic reaction, taking in energy. And if you're taking in energy, what's probably happening to disorder around you? It's decreasing, because you're probably using that energy to do what? What do chemicals use energy to do? Make new what? Make new bonds, organize themselves, become more organized. So we might say that a positive delta G oftentimes means decreasing entropy. And these reactions, for them to happen, you have to constantly add energy, which means they're what kind of reaction? Non-spontaneous. All right. If you know that, and you can do basic algebra, the Gibbs free energy problems that we have will be very easy. Let me show you an example. All right, here's an example problem. An experiment determined that when a protein unfolds to its denatured state, the change in enthalpy is 53,000 joules per mole. And the change in entropy, delta S, is 275. Pay attention to the units on that. It's joules per mole times Kelvin. And that's happening at a temperature of 20 degrees C, which we're going to write down as what? 293 Kelvin. And what we want to know, first of all, is what's delta G, and then we've got some questions about it. So I'm going to go to a blank slide where I can do a little work here. Remember that this is our equation, delta G, Gibbs free energy, equals delta H, enthalpy, minus Kelvin temperature times delta S. Our problem gave us all those things. It's just a matter of plugging and chugging here. The enthalpy was given to us as 53,000. Temperature, they gave it to us in Celsius, but we converted it. 293 Kelvin. And the change in entropy was given to us as 275. And those are the units. Now notice that what happens to the kelvins? They cancel. So now we multiply this out. So 293 times 275. Subtract that from 53,000. And we end up with an answer of negative 27,575 joules per mole. All right, now the key thing, the numerical answer is not going to help us a whole lot. What matters is the sign. So that negative number, what can we say about this reaction since it's negative? All right, I heard somebody say that it was spontaneous. It increases entropy. And what other thing can we say? It's releasing energy, therefore it is exergon. That's as hard as the math gets on us. Everybody ought to be able to handle that, right? This equation is on your AP biology formula sheet. You can use it on the test. You can use it on any test that we have, because it's on the main test. You just got to know the formula. Questions? All right, where are we at on time? All right, I'm going to stop there. I'm going to show you a little video clip first.